Right, okay, so welcome everyone. Welcome everyone to this new video where we talk about stuff on the board. And in this particular case, we'll talk about something that uh, sometimes is not much discussed in traditional curricula in physics and applied mathematics. And that's a theorem that is due to, at least attributed to Bohr and Van Leeuwen, although many people really try to push that this is Van Leeuwen really who did most of the work. And in particular, it has been heavily discussed by Van Vleck in a book written entirely on magnetism and electricity, and in particular susceptibilities, magnetism and electricity, in 1932. And so what I'm going to discuss here is essentially part of the discussion that is in that book, that also sometimes can be found not necessarily in electrodynamics text, but it can be found in statistical mechanics text, some of them that are going to discuss these things. And the reason why is because we try to understand how magnetism can occur in matter. And as you know, if you try to have an understanding of where magnetism comes from, you need to look at how the microscopic features are going to give rise to macroscopic ones, like magnetism. And so that's why people need to use statistical mechanics, especially because in real life, you always have some temperature out there that is going to interfere or to make things kind of more uncertain and more jiggly, if you will. And so that's within that particular context that we are going to discuss magnetism today. Right, okay, so the context of this discussion is the following. Um, we are going to show, or at least we are going to provide a proof a proof, if you will, that seemingly it's impossible to obtain, in fact, any classical magnetism. And that could be paramagnetism, ferromagnetism, diamagnetism, whatever you want. Actually, you can't obtain any of that, okay? And this is, as I said in the introduction, that's actually called the Bohr-Van Leeuwen theorem. I think it should be called the Bohr-Van Leeuwen-Vleck or Van Vleck theorem, because Van Vleck has actually added additional discussion and also, in fact, proof of this particular theorem and contextualize it a bit more. But okay, in any case, so let's say today I'm going to call that the Bohr-Van Leeuwen-Van Vleck theorem. What was known at the time, again, that's in the 1930s, is that if you assume that you've got particles that have a fixed magnetic dipole moment, then you're going to find out paramagnetism. Uh, yeah, that's about it. You can maybe justify a bit diamagnetism and so on, but usually at least you can explain paramagnetism. Um, Now, you can also explain via some other model, like the Ising model. Again, with existing dipoles, you can explain as well ferromagnetism and so on. But the bottom line is that this is actually possible classically. So there exist some derivations that were provided by Langevin that you can obtain classical magnetism. You can explain, you can get the correct susceptibilities, the correct dependence in temperature, and so on and so forth by doing classical statistical mechanics on existing permanent dipoles. Okay? Um, Now, the thing is that when you start pondering, and that's what Bohr and in particular Van Leeuwen did, and she did it actually in a PhD thesis. Um, when you try wondering, okay, but hold on a second, where do the dipole moment come from? And then you say, okay, well, the dipole moments, if you look at a molecule or if you look at an atom, well, if you look at a molecule, then the dipole moments are going to be connected to what the electron cloud is doing. Okay? If you look at an atom, that's going to be the same. The dipole moment is going to come from what the electron is doing and so on. And so at the end of the day, then the idea is, okay, but why should I apply the tools of statistical mechanics to the degrees of freedom of a dipole that is assumed permanent and not to the sources themselves of the dipole moment. Um, and basically that's kind of what Van Leeuwen did. And that's what we are going to do today. We are going to see, okay, let's try to apply statistical mechanics to the source of the moment, the magnetic moment, and let's see what happens. So the idea usually is to say, well, the magnetic moment is going to come from currents and things that are moving, more readily in molecules and in atoms and so on, in metals, whatever, are electrons. Okay, so usually people kind of reduce that to electrons, and that's what we are going to do today. The same thing could apply. In fact, Van Leeuwen and the general proof provided in Van Vleck is actually general. So it's for any kind of problem. But basically that's what we are going to look at. So today I'm going to simplify slightly the derivation that is given here, just because I don't want to presume a huge amount of statistical mechanics knowledge from the viewers. So we are going to limit ourselves to one electron. So let's say an electron, like as if you had strip out a molecule of all of its electrons but one, for example. Um, and so therefore we are just looking at one particle, and we are looking at electrons only. Okay. Again, that can be more general than this. It's just for you to get the idea. So first of all, what we need to do is we need to know what is the magnetic moment associated to an electron, right? So so basically, magnetic moment of an electron. So what is that? Well, in a previous video, we've actually calculated that was for that actually that we calculated it. We calculated the magnetic moment of a general current density, or the yeah. So we've got m is equal to half, and then the integral of r cross j, and then dv, okay, over some omega here, okay. So basically that's it. So that's a general expression for any j. But then the point is that, well, okay, but what is j for an electron? Well, an electron is here considered to be a point particle, so it's going to be minus e, and then usually what people do is that they say that this is minus. In fact, I'm going to say something a bit different. At least I will do in two steps. So usually when you don't have diffusion, okay, when you don't have diffusion, so diffusion currents can exist, and that's what happens, for example, in semiconductors. But if you don't have diffusion and you've got so-called drift velocity, then J is equal to rho and then times V, where V is a velocity, so-called drift velocity of the particle, so under some force. Okay, so I'm going to assume here that that's the case, that the electron is under some electromagnetic force, and so it has a velocity associated to that force. And then rho is the charge density which is being transported at that particular velocity. Okay, so that's what I'm assuming here, and rho turns out to be, in our case, minus e, and then delta of r electron minus, sorry, that's the opposite. It's actually delta of r minus r electron. Okay, so what I'm saying here is that, and then times v, of course. So what I'm saying is that I've got something called the position of the electron, and then here r is the thing I will integrate over. Okay, and I'm just saying that I have basically a point charge at which has magnitude minus e, that is exactly at re, and then there is here the velocity v, which is a derivative of re. So by the way, I need to say here somewhere that this is the derivative of re. Okay, so what happens is that when I put this delta function in there, what I'm going to get is basically the integral here is going to substitute just all possible r in the integration, including this one, by re. So I'm going to get that this is minus e over 2, and then I'm going to get re, and then cross re dot. As simple as that. Okay. So what we do from there is simply that we are going to have so I can provide the entirety of it, if you will. So m, and then we can evaluate this. So that's minus e over 2, and then I'm going to use the traditional x, y, z kind of technique. So here we've got x, x, y, z, x dot, y dot, z dot, and so what we have is minus e over 2, and then we have not sure exactly how to put this. I mean x, so that's y z dot minus, so y z dot minus z y dot, and then minus e over 2 y, and then this is zx dot minus x z dot, and then minus e over 2 z, so that's this one, so that's x y dot minus y x dot. Okay, so these are all the terms that we need to calculate. Now, the thing that Van Leeuwen does is basically trying to look at each of these terms. So essentially what we are going to get is we need to evaluate the expectation value and so what I mean by that, so that's aka the average of this quantity, of a quantity of the form xi and then x dot j. So that's what we want to evaluate. We want to evaluate that particular quantity within so-called classical statistical mechanics. Okay. Now, for those who don't have a lot of background in statistical mechanics, the main idea is that the weight, the probability weight, of a state, of a configuration, let's say, is going to be proportional to exponential of minus the energy of the state you're in, okay, divided by kBT. And kB here is a Boltzmann constant, and T is the absolute temperature in Kelvin. And basically, that's the only thing that you need to know. The configuration here, what I mean by configuration is, or in fact, I should call that really microscopic state, that would be giving the position and the momenta. And in this particular formalism, we focus more on momenta. And so the way this is going to read is like so. The xi xj. So here this is the average, and that's going to be proportional to the integral. And the problem is that I need to integrate over all possible, again, configurations of a single particle. So in principle, that's all positions and all momenta values. So that's going to be exponential minus, let's say, e over kBt. And then we are going to get dx. For example, we are in 3D here, so that's dx1, dx2, dx3. So that's x, y, z, these guys, and then the corresponding momenta. So dp1, dp2, dp3. Okay, and I forgot, obviously, what I shouldn't forget. I forgot the term to be averaged over, and so that's xi x dot j. Okay, now so you see we are just taking an average here. That's basically what we do. Now the thing is that the energy here, I gave it the denotation E. Okay, usually it's called H, but the bottom line is that actually you can say that x dot j, we know that this is equal to dE over dpj. Okay, so whatever j I've chosen in this list, it could be j is equal to 1, 2, or 3. I could choose whichever. I know that this is going to be equal to d over dpj. Okay, so what that means is that here I've got d dpj exponential minus e kbt. So what that means is that whatever happens, I'm going to get for this particular integral, xi xj is going to be proportional to, and then what I'm saying here is that if you've got here a derivative of e with respect to p, and you've got an integral over a corresponding p, then basically you can integrate it right away, at least with respect to that particular variable. And so what that means here is that I'm going to have basically this quantity, so exponential minus e over kbt, and that's integrated over the limiting value of p. So let's say I'm going to say p min versus p max. So there's p min, p max, and then there is the rest of the integrals. I mean, we should not forget that there is the rest of the integrals. So then there is xi exponential minus e, and then kbt, and so on. But then there is all the rest here. So put 3 dots there. Okay, but the bottom line is that you're going to have this. I need to, it's proportional to that. There is a minus sign coming in because if you differentiate with respect to p, you're going to get a minus sign. So there should be a minus sign, there should be a kbt, but I keep things proportional here. Okay, now the thing is that what Van Leeuwen said, and Van Vleck actually highlighted, is that because here you already have this term, okay, because you have this term, I'm just trying to see whether I made a mistake somewhere. No, my bad. This is so that, I mean, this is correct, but however I need, but that's, so this is correct, but this is incorrectly written. So because I can write this equal, let's do it a bit more slowly. So I've got this. So then I write xi x dot j So that's x dot here. Because I write that, so that's proportional to. And what I do is that I keep all the integrations here. So that's xi. And then I will put all the rest. So dx, so all the dx1, dx2, dx3 are there anyway. Then I put all the, so I would put, I don't know how to call them, but basically dp, let's say, so here this is j, so I could say dpk, dpl, and k and l are different from j, so let's put it this way. And then I actually put d over dpj, and then exponential minus e over kbt. Okay, so that's how you do it properly. Now, essentially, I can integrate that guy, and so that's going to be proportional to xi, dx1, dx2, dx3. We still have dpk, dpl, but I forgot here to integrate with dpj. And I've integrated over dpj, so I'm going to get then the exponential minus e over kbt, and then from p min to p max. So that's a proper way of doing it. So what that means is that here you would get still a function of all the rest of the variables. So of course you can't put it outside of the integral. It was a mistake on my part. And then the insight from Van Leeuwen is that if E becomes infinite, so if E becomes infinite when P equals, so when Pj equals P min or P max, then basically the term in brackets becomes zero because it's exponential minus infinity. Okay, so then exponential minus E tends to over kbt tends to zero, and essentially you're going to get that any term in bracket like this, xi x dot j, is strictly equal to zero, no matter the temperature you look at. Okay, and basically the point is that this is actually usually the case. The p min and p max that people are looking at usually in classical statistical mechanics are minus and plus infinity. And if you take the traditional kinetic energy, even in relativistic theory, then when p tends to infinity, the whole energy tends to infinity as well. Okay, so that's essentially what it says, is that if E becomes infinite, then you've got that. There is a more detailed and intricate derivation that can be done by writing explicitly the energy. But again, the insight from Van Leeuwen is that in fact it doesn't matter how you write the energy, as long as you've got this constraint that when E, when Pj is equal to P min or P max, the energy is infinite, then automatically you get zero. Okay? And so because any of these terms is going to be zero, it follows that any of these terms are going to be individually zero. And so the conclusion is that there cannot be any, let's say average, let's call that at least average magnetic behavior and what I mean by that is a magnetic moment, non-zero magnetic moment, from the classical theory. Okay, and that's the reason why this is quite fascinating is because the same issue does not happen for electrical dipoles. Okay, so it has to do with magnetic dipoles only. So basically that's it. Now the solution, at least the current solution being put forward, is that you need quantum mechanics to actually get any form of magnetism. Okay, and there are various reasons why that's the case, but basically we'll discuss that in another video. So I hope that you found this insightful. I have tried to keep it as simple as possible. I did make a slight mistake here, but it's good to see these mistakes because then I can show you how to, how to do it much more properly afterwards. So basically that's it. If you've got any questions on this, please let me know. I will probably go back to discussing this at in some later video, just to see whether there is any caveat or whether some other stuff can be said about this.